Here we talk about quantum flag manifolds and non-commutative geometric representation theory. Please, the floor is yours.
Okay, so first of all, I guess this is how to put it into the context of the school in carton geometry. These are, Q deformations, which I will explain in the next couple of slides, of flag manifolds, which of course is the central part of parabolic geometry, the special case of carton geometry. It's also the non-commutative geometry that Jan was speaking about at the start of his lecture, and it also is an opportunity to promote. Next week in Prague there will be a companion training school to this training school dealing on quantum group, non-commutative quantum analogues of stuff you would have been hearing about this week. So I'll give a talk here about general introduction to what quantum groups are. Many of you heard this talk and even the newer stuff that comes afterwards, and the newer stuff that comes afterwards, which is recent work that should eventually appear in the next month after a long time. Okay, so let's start off. The way maybe I will have been introducing quantum groups over the last couple of lectures, or of course the last couple of talks that I've given, is this very concrete presentation. So if you take something like a Q integer, what is a Q integer? It's just going to be a series like this. It's a geometric series, simple, for some real number Q. And we see that when Q is 1, what this reduces down to is the ordinary integer. Okay, a very elementary idea. Why would one look at these things? Well, you can do a lot with them, you can play with them. For example, once you have a quantum integer from this, you've got a natural definition of a quantum binomial coefficients. And these actually appeared way back in the work of Gauss. And that somehow in combinatorial questions that he was looking at, these quantities started to arise. And they appear very naturally. I heard a talk, it was probably last year at this stage, where somebody said they even start to appear back in the work of Euler. So this deformation of integers, a series like this, is it's a very old thing and a very natural thing that has been around for a long time. You can build, so this is really just the second step almost. From this, there's a whole sort of industry, and there has been for a long time, of taking notions that we would understand in mathematics and trying to Q-deform them in this sense. So there are things like Jackson's Q derivative, the sort of Q-deformed version of the elementary integral and differential calculus, Q exponentials, and then up to things like the theory of Q special functions. There are lots of, and again, they're preserving this deep combination or relation to combinatorics. Okay, so this is what's kind of known roughly as Q analysis. Let's put that aside for 1 second, and let's go to something closer to the topic of this talk. At GB, a complex semi-simple Lie algebra. As we know, these things, complex semi-simple Lie algebras, are somehow Z structures. I don't mean anything precise in this sense. Just mean that we know when we look at the classification of these things, when we look at the representation theory, they're integer valued. So, you want to look at least in the finite dimensional case. So, for example, when you're classifying the representation of these things, you're going to get them in terms of integers, tuples of integers, or dominant weights. When you're looking at root systems, for example, these are all very integral notions. So the integers are all over, have a fundamental structure in the theory of complex semi-simple Lie algebras. So what we're going to do is try to now naively ask the question, okay, so sorry, this is, think of this representation of the universal enveloping algebra as another idea. You see integers all along, binomial coefficients, and so on and so on. So the very naive idea is that can we take the integers that appear in complex semi-simple Lie theory and can we do this similar process of sort of Q-deforming it and finding this quantum analog, just taking these Q integers, taking all of the integers that appear inside, and for example, the representation of the universal enveloping algebra, replace these by quantum integers and then see what happens. Okay? It's a very naive, not very simplistic way to introduce these things, but hopefully maybe it's helpful. And the answer is yes, we can. And this is what we actually get. This is what Drinfeld and Jimbo found back in the late 80s. This deformation, so you see here that roughly speaking, okay, there are subtleties involved here, putting Q equal to 1, but roughly speaking, once you take the limit as Q goes to 1 in the correct way, this will reduce down to the universal enveloping algebra, or more correctly, a cover of the universal enveloping algebra of G for our semi-simple Lie algebra. So here the A by J are the Cartan matrix, and yeah, this is, I guess, something you're mostly familiar with. And this works, and it was not discovered like this. It was not that they actually, is the way that I've presented it here, that Drinfeld and Jimbo were looking at Q integers and they decided to cutiform it. It was really coming out of quantum integrable systems that these objects sort of naturally arose, and then afterwards they discovered, when they were formalizing everything, that the Q integers are all over the place, and it's a simple-minded way to understand it, but for an introductory talk to this thing, I guess maybe not so bad. So why are these particular choices of Q and so on? You really can't see that from here. So maybe the way that I will justify it is that it is really a very distinguished it is a very distinguished way to Q-deform this. It has many important properties. So if we look at the category of finite dimensional representations, it's actually equivalent. So for every finite dimensional representation that you have of your classical Lie algebra, there's a corresponding representation of this, and it all works nicely. Moreover, this thing has got a Hopf-algebra structure. A Hopf-algebra structure, if you want to think about it in the categorical terms here, in terms of these category of finite dimensional representations, it means that you can actually take tensor products of these representations, roughly speaking. Which is to say, okay, if you don't know what a Hopf-algebra structure is, it means that this thing has got a tensor product. And the category of representations is the same, so you don't really, finite dimensional representation, you don't really get anything new there, but the tensor structure, the way that you can make tensor products of them, this is different. This is genuinely something new. It's Q-deformation of this monoidal structure. This is what leads into, this is how you get solutions of the Yang-Baxter equation, and that was the original place that it came from in statistical mechanics. So okay, this may not be very clear, or clear at all, why it actually takes this form when we put in the Q integers, but it has all of these nice properties. I should maybe tell a bit more of the truth. It's not the unique way, the unique Hopf-algebra that will realize this category. There are different deformations that you can find that reproduce this monoidal category, but in some sense it's the simplest one. So in some sense this is actually the thing that we're studying, using this realization of it as the modules of the Q-deformed algebra. And this is somehow the simplest deformation that's there in a rough sense, so that's of course the one that we look at. But this is really the fundamental thing, this Q-deformation of the monoidal structure. So, they've also found a lot of applications since then, polynomial invariants of knots, because they're all connected to braids, braidings, and so on. This and knot theory is a solution to the Yang-Baxter. The representation theory, afterwards you can produce the theories of canonical bases that allow you to actually make statements about classical representation theory and decompositions of tensor products and combinatorial questions like this, or also to von Neumann algebras, more in the spirit of what was spoken about in the last talk, the end of the last talk. Okay, so hopefully some motivation for why these things are actually important. In the quantum setting, though, what we have is this Q-deformation of the enveloping algebra, but not of the Lie algebra itself. Okay, one would expect that at this stage this has been sorted out, but in fact it hasn't. It's still, there's a lot of progress in many results and much discussion of the question, but I think it's generally agreed that it's not totally understood or settled. What we do have, though, a very important result, and this actually is the result upon which this canonical basis that I spoke about earlier on rests, is that we do have a Q-deformation, the quantum analog of the classical Poincare-Birkhoff-Witt, the PBW theorem. This is due to Lustig, and what Lustig did realize that on here you don't have an action of the Weil group, because roughly speaking, one part what happens in the deformation is that inside in the Weil group for these Lie algebras, classically the Weil group you would square an element and it gives you the identity. This does not hold in the quantum setting. Roughly this is one of the things that disappears. You go from Weil groups to braid groups. In the A series case you would go from the usual symmetric group up to the braid group, this Artan braid group. But he took that into account, found an action of the braid group on this, Q-deforming the classical structure, and again, more technical formula that may not give you so much when you look at them, but the important point is that the mapping that I described determines a homomorphism of the braid group into the algebra of homomorphisms in universal enveloping algebra, And then what he did was he took the longest element of the Weil group, for whatever series we're looking at, and then he took the classical definition, so we did the classical representation of the Weil group, and you use this formula, then you actually reproduce all of the root vectors inside in G. All of your positive and your negative root vectors inside in G. So what he did was he took this as a definition, and then defined quantum root vectors. However, notice that classically the choice, at whatever decomposition of the longest element of the Weil group you take, you're going to produce the same root vectors, the usual root vectors that we know inside an early algebra. In the quantum setting, it's different. And in fact, it is really determined or depends upon the choice of reduced decomposition. In fact, to be more precise, it's commutator classes of the longest element of the Weil group. Sorry, commutator classes of decompositions of the longest element of the Weil group. What do I mean by a commutator class? It means that you're allowed to change one decomposition into another decomposition if you can just swap elements. When they're far enough apart, the elements of your Weil group commute. So if we perform one of these commutation relations and transfer a reduced decomposition into another, that doesn't actually change the quantum root vectors that you get. If, however, we perform a braid move between one choice of reduced decomposition to another, then that actually does change it. Okay, so this is what actually gives you different quantum root vectors in this commutation process. So in most of the literature, when you look at it, you see people don't really take too much care about what reduced decomposition are. You see, you make a choice, and then everything kind of works along, irrespective of what choice you've made, and you can kind of do it in general. So what we were interested to see is to take a more geometric, non-commutative geometric approach to this, and to see if we could actually start to tell the difference between these reduced decompositions, the difference between the positive root vectors and negative root vectors inside in the quantum universe and developing algebra, using some geometric approach or geometric ideas. But an important point, I should mention before we do that, is that this result of this definition of these quantum, positive and negative quantum root vectors, why it's important, one justification for it, why he was actually looking at it in the first place, is that it gives you a PPW theorem. Okay, it's a little bit strange because the K's and the classical carton, the approach between them is a little bit tricky, but you've got this PPW style theorem for these things, and that is the starting point of canonical basis, just using a quantum Vernon modular approach, and that's an extremely important result in the theory of quantum groups, and particularly their applications to classical representation theory. Okay, so maybe let's just have a look at a simple example so you can see what these things look like, because the general formula that we gave are not so instructive. So here, for the case of quantum SL2, the Weil group is S2, so the longest element is just going to be the entity element from the corresponding pair of positive root vectors is E. That's not particularly interesting. For the case of SL3, things become more interesting. You get more insight into what's happening in the in the quantum setting. So we see that the longest element of the Weil group is given by S121 or S212. And these two things, to change between these two reduced decompositions, you see you have to use a braid move. So these do genuinely give you two different choices of root vectors. And in fact, what happens is that we see classically the root vectors would be E1, E2, or simples, and then they're simple generators, and then a commutator bracket. But now, because we're in the quantum setting, we get a Q, but there's somehow no reason to choose Q over Q inverse. Everything should sort of be symmetric with regard to this, and that's exactly what happens. These two reduced decompositions give you either a bracket with a Q or a Q inverse. So this general theory that works uniformly across all of the series, when you bring it down to some specific examples, it's quite concrete. Can also, when it go up one more and look at SL4, and we see that the Weil group here has 8 commutator classes of reduced decompositions. Now what I've done is, just to save space, you've taken so in this case, of course, with the A series, it's the symmetric group. I've taken the generators of the symmetric group, and instead of writing S sub I, I've just written the number itself. So here, these guys at either end are sort of the nicest decomposition that you can have, and then by successive applications of the braid move, you can go from one to the other. And somehow you see that there's more, it's these guys in the middle here that are the more complicated reduced decomposition, whatever that means. Okay, so then what do the root vectors look like for these? Okay, there's a question of space, so I've sort of condensed it here, which you can see. Yeah, so something I should mention is that here we of course have this automorphism of the symmetric group where we can change the first and the last generator, the second and the second last, and so on, just by sending 1 here, 1 to 3, and 2 is fixed. Okay, so nothing actually will change with respect to this automorphism because it's just a labeling. You're changing the order of the labeling of the Dinkin diagram. So in fact what we can do is we can forget about these guys over here because any property of them will be understood from the properties of the corresponding one at this side. So that's why it will reduce down to this 6. See, this is the nicest one up here. Everything is ordered. So sorry, the safe space as well, I wasn't able to put in the Q's. I've just put a minus when it's Q inverse and a plus when it's Q. Okay. So you'll see here that in this, the nicest one, you've got Q inverse and Q inverse and Q inverse and Q inverse. Everything is uniform. But as you've moved further along with performing more braid groups and your decomposition of the longest element, it starts to get more mixed up. Pluses start to appear, and you see that here you're counting down, so it becomes 3, 2, 1. Sometimes here the order of the counting reverses, so it becomes more sort of chaotic as you go along, and this is actually what happens in higher orders as well. So the question now is, can we use some sort of non-commutative geometric idea to distinguish between these different decompositions? Okay, let's try to put more meat on this idea. So classically, the space of positive root vectors is isomorphic to the anti-holomorphic, the complexified tangent space of the full flag of G. Okay, so you just take this, it's a complex manifold, complexify your tangent space, which will be the positive and the negative root vectors, and then it's going to decompose into the 0, 1 and the 1, 0 part. Okay, just like any complex manifold. Here we're just going to focus on the plus because it's the pieces that we've actually worked out, we've done the calculations for at the moment. So one can now look at these root spaces, or say these spaces here, tangent vectors, and ask, do they behave in any sense like does the fact that they're a tangent space classically have any analog in this quantum setting, in this Q-deform setting? So can we find a generalization of this, and can we use it to probe Lustig's construction? That's the idea. First of all, though, we should see what a full quantum flag manifold is. I've just defined so far or presented the universal enveloping algebra, but in fact there's a dual notion, dual pairing of Hopf algebras of the coordinate functions, and as Jan was saying at the start of his talk in the non-commutative setting, you've sort of forgotten about the space and you're just looking at algebras that behave somehow like the algebra of smooth or algebraic functions on some variety. And here what we're doing effectively is U cube SUN, you sort of take the Peter Weil presentation of this classical ring and you use it almost as a definition, as a means of going from the universal enveloping algebra, of dualizing the universal enveloping algebra to this Q deformation of the coordinate algebra. And it's quite formal, works at the general level of Hopf algebras. It's quite easy to go from one to use the universal enveloping algebra to produce quantum algebra functions, representative functions. And from this we have an action of the cartan or the quantum cartan inside of the quantized enveloping algebra that will act in a very natural way. And then you look at the space of invariance of this, and this actually gives you a direct Q deformation of the functions on your classical full flag manifold. Okay. So it's kind of fast what I'm saying here, but basically classically your algebra functions on full flag manifold can be understood as a sub-manifold of SUN, or in general O of G, and that basically carries over directly. Okay, and here's the definition written out. What's important to observe is that these functions, the way that we've defined it, we're quotienting on one side, so that means that we've got an action on the other side, and this gives us a symmetry, and the idea of the school here is that any sort of geometric structure you would want, you should have a symmetry acting on, and all of your structures should be preserved by this symmetry, and that's exactly what we want to do here. If we're going to build up some sort of, from this tangent space, some type of Q deformation of the de Rham complex, or the anti-holomorphic de Rham complex of our flags, then it would want to preserve the group structure, or the quantum group structure, the quantized enveloping algebra structure that we have here, just as we've seen many of the talks up to this point. So, can we build a differential graded algebra which cutiforms the antiholomorphic, this subcomplex. We're just focusing on this because that's, as I said, what we've done the calculations for at the moment, and it's already sufficiently complicated, but there's no reason why we can't do the whole thing that respects this action. So, more formally, for those of you who know about this, who know a little bit about Hopf algebras, one would want that this differential graded algebra is actually a relative Hopf module. What is this? So Jan spoke about associated bundles over a homogeneous space. This construction, this equivalence between homogeneous vector bundles and representations of the isotropy subgroup has a huge extension up to the general setting of Hopf algebras, and it's expressed as something what's called Takeuchi's equivalence for relative Hopf modules. So there is a very formal setting in which we can understand this, a formal setting in which we can understand our differential graded algebra, the one that we want to construct, as a non-commutative, as a quantum associated bundle in direct Q deformation, direct, in fact, Hopf algebra generalization of the associated bundle construction that Jan presented to us 2 days ago. So that's how we want to do it. We want it to be a non-commutative associated vector bundle over our quantum homogeneous space, our quantum flag manifold, the subalgebra of the functions, subalgebra of OQ SUN. So sorry, there's a Q missing over here. It's the left covariant first order differential calculi. These are just going to be, what does that mean? It just means, first of all, we're going to try to construct the degree 1 part of our differential graded algebra, and then once we've done that, we'll extend up to the whole thing. So start on degree 1 and then go up. And in fact, this is something that people have thought about for a long time. It goes back to the work of Voronovich in the 1980s. It was then afterwards built upon by people like Harmissen and Heckenberger and Kolb and so on. I won't explain these formulae here too much, but there's an easily verifiable set of conditions that you can ask for these candidate tangent spaces that we have to satisfy, that we can just check by calculating. And if they satisfy these conditions here, so that the triangle here, the delta that we have, is actually the co-product of the Hopf algebra, if that helps. If it doesn't, basically I'm saying this question that we're asking, do these things look like non-commutative tangent spaces? There's a whole theory there in the context of this non-commutative or Hopf algebraic associated vector bundles to take care of this, and we can verify it, attempt to verify it. Explicitly what happens is that if it satisfies these conditions that we have up here, whatever they mean, then we can take this tangent space and we can form this Hopf algebraic structure, this Hopf algebraic construction. What does this mean? This basically also goes back to what Jan was talking about. These things are a deformation of the sections. It's an alternative, if you go to the classical setting, it's an alternative presentation of the module of sections of the associated vector bundle. Well, you can kind of see, we saw here on the board there was the X and we had the representation and we were quotienting by this representation. That's what's going on here. Okay? It's a box, it's what's called a cotensor product in the language of Hopf algebras, but don't worry so much about that. Just saying there's direct, natural Hopf algebraic way of describing the sections of the associated vector bundle, and this is what it is. And then what we're going to do is, once we have the tangent vectors, the vector fields, then we just dualize. Okay? There's a lot going on with the just, but it's all very well understood and has been understood for a long time in simple examples. And effectively what we're doing is trying to extend from these simple examples to more complicated situations. And what happens, what's special about this dual is that we have a map from the functions into this. It satisfies the Leibniz rule, and then this thing is generated as a left or as a right module with respect to these things. It's a first order differential calculus, as they say. So, what happens? In fact, if you know what the Hopf algebra structure of UQSL2 is, I didn't define it because I didn't really have time, but in fact, it looks like this. So the co-product is E. Let's say in the classical case, so for the universal enveloping algebra, the classical universal enveloping algebra, this is a Hopf algebra structure. And it looks just like this. To some extent, this is actually encoding the Leibniz rule classically. What happens in the quantum setting? Well, it gets twisted. Okay? And you get a K on this, the Cartan side on this side over here. And in fact, if you go back to the formula that we had for a tangent space, you can conclude immediately from this that in this simple case it actually gives you a tangent space. So this whole construction works out and you've got an associated differential graded algebra Q form. For UQSL3, yeah, so for UQSL3, wait, no, sorry, I think it's jumped directly to 4. Sorry, this is 4. I'm after skipping 3 because I think for a case of... remember that we had all of these reduced decompositions of the longest element of the polygroup. This was the commutator classes of elements. Let me just go back for a second so you can see in mind. This here, we're now going to look at the space of quantum root vectors for each of these decompositions and check if it actually satisfies the tangent space condition. And it turns out, so what do I mean by left and right? What I mean by left and right here is that, in fact, you could reverse the side in which we quotiented, took the quantum analog of quotienting to produce a homogeneous space. Basically, where I'm quotienting on the left with a subgroup, or I could quotient on the right. Two things, the spaces are going to be the same and so on. And that's what it's going here, is saying that when you're on either side, in these nicer decompositions, the one somehow at the extreme where we've got most coherent presentation of the reduced decomposition, most coherent choice, then it will work whether or not you're taking the quotient on the left or on the right. When you start to go into these ones in the middle, these ones that are a little bit more chaotic, it just works for one side. Okay, so here, this is where we're already seeing a difference. So for the case of SL3 that I left out, basically, you've only got these two decompositions. So you've somehow got just two nice decompositions on both sides, and they're both two-sided, they both work. So we don't really see anything there, just like for SU2. But by the time we get up to SL4, we're starting to see that some of these choices of reduced decompositions behave better in the quantum setting than others. So separating them out somehow for the first time. If we go up to the case of SL5, I can't, you've got, I think it's 62 commutator classes. This is actually a combinatorial question, an open combinatorial question to understand how many commutator classes there are of these reduced decompositions. It's known up to SL7 or 8 or something like this, and after that it's not. Well, here it's something like 62 if I recall correctly. We're just going to give the ones to the left-hand side of the diagram. So before, for SL4, we had this. Okay, here for SL5 it starts to grow, and you have a far larger number, and you've got things that are somehow inside in the middle now, not just on the edge. Okay, but you can amuse yourself by trying to go from one to the other using the brain moves, and you can continue on. And what happens is that now these things that are in the middle are even worse somehow, and they don't satisfy this tangent space condition either on the left or on the right. Meaning that these are from this non-commutative geometric test that we've given to these reduced decomposition. These ones in the middle are very badly behaved. Again, these ones on the outside are sort of, they're not as good as the extremal ones here, but still things sort of work. So that's what we're going to do. Well, actually, in fact, I haven't. This is an older version of the slides. I still have, we've recently proved the results, so I haven't written it up here. But in fact, it turns out that when we're going to take the maximal, this extension from the one forms up to a whole DGA, these guys here also have non-classical dimension. So somehow, if you just look at these ones on the edge for the degree 1 part, then this sort of, there's still something there, still something you can work with, still this non-commutative geometry that you can try to examine it. But once you go up to the higher forms, they also have sort of degenerate behavior, so they also somehow need to be discarded. We don't have a result yet for all of SSN, for all of the AN series, to say that it's only these two ones at either side of the decompositions that actually work, but we conjecture in fact that this is true. But for the work, that's a question for the future, where we need some more combinatorial tools, I think, to actually be able to answer the question. So for the moment, for the rest of this talk, what I'm going to do is to just restrict to this nice decomposition that we have here. There is actually a formal sense of nice, and there's Peter Littlemann's work and so on, that works for every series, for the A, B, C, D, and the exceptionals. And we're sort of loosely conjecturing that this is what will happen in the other series as well, but this is not, question is not yet been properly addressed. So the next step in this, as I was just mentioning, is to try to extend from your one forms up to the higher forms. And basically, it's a result, an abstract result about differential graded algebras, that once you have sort of one forms like this, so something that's generated as a left and a right module by D of A, where A is your algebra, over which you're building it, the degree 0 part, then you can always extend up to a differential graded algebra. And there is a unique one in the sense that the unique largest one, and this is a universal property that uniquely defines it. So in fact, once you have your one forms, going up from there is surprisingly not that difficult. You're really not defining the extension up as some sort of exterior algebra. It's a different equivalent in the commutative setting construction, but reduces down to the same thing in the classical setting and gives you a differential graded algebra with summum maximum. So what can we give a description of for these the quantum one forms, for the non-commutative one forms, for these decompositions, for the flag, can we give a description of what this is? For that I'm going to use a small little bit of Lie theory and to say roughly, okay, given there's about 8 minutes left and this is a little bit technical, let me just give the basic idea is due to work of Paulo Papi, if you have a reduced decomposition of your longest element with a Weyl group, that then puts a total order on your space of roots. So in general, a positive roots. In these in general, we know we've just got a partial order. There's no canonical way of putting a total order on this. But if you make a choice of reduced decomposition of the longest element of the Weyl group, there is a corresponding total order. And in fact, that those total orders which arise from reduced decompositions, can be characterized in the equation that's up here, and these things are what are called convex orders. So what we're going to do, of course, is take the reduced decomposition that we've chosen at the start to give our quantum root vectors, and we're going to use that to put an order on our roots. And let's just look at it roughly. If we imagine this is going to be SLN, so it's going to be a trace-free matrices, and we've just got our positive roots are going to live up here. Okay, so I've just presented them like this, as I haven't put in the brackets. And this, our reduced decomposition, this is actually the order that gives it. So these are our simples, they're E1, E2, E3, and then it's going to up like this, or alpha 1, alpha 2, alpha 3, I guess. Okay, that's just what it looks like concretely for this instructive example. And then what we can do is to show that, as I had written before, this maybe it's not explained there as well as it should be. We've now got our omega, I guess it's 0, 0 bullet, this Q deformation of the anti-holomorphic part. This is an associated vector bundle, quantum associated vector bundle half, associated vector bundle. So what we're going to have is it's going to look something like this, and we're going to have an algebra over here. Okay? So in the same way that, this thing classically, our one form is an associated vector bundle, our higher forms are an associated vector bundle. You take the direct sum of all of them, and this is going to be, again, an associated vector bundle. And it's basically induced by an algebra over here. And it would just be, in the classical case, the exterior algebra of your inducing representation for the one forms. Okay? The space of positive roots, or the dual, I guess, in this case. And in the quantum setting, what we get is when we perform this sort of universal extension up to the Weyl calculus, is that we get this Q deformation of the exterior relations. And it's done in a I should write here, this mu is shorthand for Q minus Q inverse. Okay, so this is sort of a constant that appears all over the place when you're looking at Q integers. And you see that when Q goes to 1, this thing is going to disappear. So whenever you have sort of these quantum terms that appear in the setting of quantum groups, they'll quite often be preceded by one of these. And then, of course, when Q goes to 1, they all disappear, and we just get the exterior relations. But what's sort of fascinating is that the quantum terms will appear inside of this Q-deformed exterior algebra. It's really tightly constrained by the form of the roots. So here, this is the usual partial order that we have. And if, sorry, there's a typo here. There should be alpha and beta are equal to 0. Yeah. So these should be 0, and they should be comparable with respect to the partial order. Okay. When this happens, you're allowed to have the Q form. There's space enough. The root system allows enough space for this quantum term to come in. When in all of the other cases, it's not, and it's just this direct Q deformation of the usual Grassmann relations. And here I should mention the bracket that's happening here is just going to be the usual inner product in the associated root system. Okay. So this very concise, nice relation, Q deformation of the exterior algebra coming from our idea to choose or to examine the positive quantum root vectors as if they were a tangent space for some non-commutative differential graded algebra. This is what we get out of it. And you can in fact, by an application of putting a filtration on this and looking at the associated graded algebra, you can see that this actually will have classical dimension. And this does not happen in these low dimensional cases for the terms that are around the outside, the ones for which we still had at least a left or a right tangent space. This does not happen. You end up getting graded relations, and these things are no longer a classical dimension. So let's quickly have a look. Maybe let's go on to the next one because we've got a bit more of an idea here. So I'm going to have arrows pointing between dots. So we've dualized everything. We're no longer in the root vectors themselves. We're no longer up here. We're dealing in the dual tangent, cotangent space. So we go lower triangular. Okay, believe me, passing from tangent to cotangent means that we should flip not from upper triangular but to lower triangular. So between the roots that we have here, root vectors, I'm being a bit careless. We see that if the pairing of them between them is going to be greater than 0 precisely, if the relationship between them is this is a completely classical statement. Less than 0 if it looks like this. And in all of these cases, if you write them in the order of the arrow, it just becomes a Q deformation. Okay. However, this one, we have the quantum term that we have here. There's just for SL4, it's to be SL4 again. There's only one pair, and it's the first time it happens, the first order for which it happens, pair of roots for which we have a 0 pairing and they're comparable. And it's precisely the relationship between these roots here. And okay, over here when it's 0 and the wait, sorry, this is switched around, so this should be not comparable and this should be comparable. But here we get the quantum term. This extra quantum term then is going to be the product of these two things here. And that's what happens in general. It's when you have the two roots like this that are, 0 pairing and they're comparable, then you just sort of complete the square, the rectangle, and you get this extra quantum term, and that's what's happening down here. So the alpha prime is this and the beta prime is this guy. Okay, so it starts to finish up. These things form a Frobenius algebra. We won't have time to go into this, but maybe a question you would ask as well, okay, we've looked at these things, we've looked at the family of these Lustig root vectors, quantum root vectors. We've seen that certain of them, two distinguished guys, behave very well and have an associated differential graded algebra, differential calculus that behaves very much like the classical case. Is there something then that we can do maybe to make use this to give, for example, geometric realizations, non-commutative geometric realizations of the representations of these quantum groups, in this case of UQSLN and Ln plus 1? Can we realize the representations that we have using this geometry? And in fact, we have a direct Q deformation of Borel-Bay for this. So there's a lot of stuff here that I'm not explaining, because I won't have time. But we have, over these flag manifolds, we have invertible modules. Okay, and if you know a little bit about the Swan-Serre theorem or the Serre theorem, you know that vector bundles correspond to projective modules by taking the space of sections. If your module is invertible, classically that's the same thing as it being a line bundle. So you can classify the associated vector bundles for the one-dimensional representations. Everything is the same as in the classical setting. You get the same family of line bundles and their parameters as we have here. And it turns out that if your the dominant weight, the dominant weight that we're constructing this quantum, this relative line module from, Then it also has a Q deformation, it has a 0-1 connection, it has this map that Q deforms the usual holomorphic structure of these vector bundles. And classically the kernel would be the holomorphic sections, so then in the quantum setting this becomes the definition. And it turns out that the relationship between the representations and the inducing one-dimensional representation of the torus is exactly the same as it is in the classical setting. So from this journey we've gone through, we've arrived, one of the benefits, one of the structures that we get out of this differential graded algebra, this Q-deformed differential graded algebra, is this non-commutative geometric realization of the representation theory of these quantum groups. And that, I think, is where I'll stop. This is an explanation a little bit here about what I mean by the holomorphic structure, but I'm over time. And I think for the rest, yeah. We'll leave with some questions, of course. This is just done for the A series. What happens when you go to the other series? What happens when we start to look at the negative root vectors in there as well? And we would start to get some sort of we hope that we would get some Q-deformed double complex, which in fact, initial investigations show that we already do. And what happens with all of this longest reduced decomposition to the longest element of the Lie group in the other series? We don't know yet, but yeah, it will be for future work. So thank you.
Thank you for the nice talk. Bringing some overlap to the next week conference to us here. So questions, comments?
So maybe just a simple question. So I've already asked Mauro, but I'm curious, since the last time we met, I've seen in CERN last but 1 year, the development of your project and the project of Keegan, Mauro, and Henrik. So how successful have you been with, especially with Mauro, is now in Prague, in finding some kind of intersections of?
We're getting there. So basically all of these calculi, what the guys have put together is they've done it for a general differential graded algebra. So I mean, all of these things you can ask, I mean, the jets will exist for all of these things. So the question then is try to find more concrete descriptions of what the jets look like. Things are working, but they're progressing slowly. There are some categorical problems that we have, which, well, maybe they're too technical to explain.
Was, for example, possible to reconstruct by their approach some of the results that you have obtained in your?
Not so much. I mean, somehow what's going on here is that we're actually, so the guys are starting with the calculus as a given, with this quantum non-commutative differential graded algebra. That's there, and they build up things from it. What I've spoken about today is actually a means of trying to construct examples of these things in a canonical way, in an interesting way. So somehow, once you've got this, then the next step is to use what they have to build things up. It kind of doesn't go the other direction, if that answers. But yeah, I mean, things have been busy, so we haven't had as much time as we wanted to on this, but we're getting there. We're getting there slowly but surely. These will serve as examples of what they're doing.
Yes, maybe I will add one. So I don't understand very much the last question C, because I mean it's a matter of, I don't know whether choice or something else. So in our classical parabolic or other Cartan stuff, so parabolic in that case, you rather have the positive roots in the n plus, which are the standard fiber of the cotangent bundle, and the negative ones are the tangent bundle. And actually, if you deal with complex things anyhow, so the anti-holomorphic or holomorphic complex bundle appears only when you complexify.
This is complexified.
And you don't need the positive and negative roots for that, so they are not there really.
Sure, I mean, this is definitely complexified, I guess, in the Drinfield's way everything is somewhat complexified. So what we really want to get towards is some sort of a double complex like this. So
yes.
that's why we're taking in the positive and the negative to produce kind of non-commutative Kähler geometries and so on and so forth. But yeah, you could look, I guess, at the star invariant part. I mean, yeah, you could take what you have here, but somehow we get more interesting stuff when we look at the complexified.
I mean, in the commutative approach, as I understand the story, is that if you want to see the things complex, as usually you do when you want to employ the representation theory the simpler way, then actually the right approach is to view it as real with complex structure on top of everything. So you view the groups as real groups, and then the complex geometries are simply such which have a couple of torsions and curvatures vanishing automatically, right? And so you simply allow only one part of this, also this omega 0,2 part of the curvature there, right? And so it's all the negative roots are there for the tangent directions, and the positive one for the cotangent bundle, and the Cartan-Killing form is just the dual parallel. Here, that's it. What's in the cumulative picture.
You're, I mean, probably right. And as we understand more and more, and I understand better the classical picture, we'll probably be able to give a better answer to this. Yeah.
One problem in the puncturing case is that you have somehow a freedom of choice coming from the choice of a decomposition. And one thing that is not clear is, okay, I fixed the decomposition, I got my positive root vectors. Which negative root vectors should I take in correspondence? Are they the one corresponding to the same decomposition? Is there somehow a notion of inverse decomposition? That part is not clear to me. Maybe it's more clear to you, Reamonn. But
I mean, yeah, this is less.
There are these kind of questions that are related to the combinatorics of the breaking, which is really quite.
I mean, as well, I guess, to get all of this to work, because we're feeling in the dark a little bit, so you want to do something where lots of things work that they shouldn't work, so you know that you're in the right direction. And looking at the complexified is one way, because there's so much structure that you can ask for. But once we do actually understand things better, we need to go back and ask questions. Just like
my question stemmed from not understanding anything, right? So I just was confused why there should be this blend of the positive and negative roots to get the two parts of the complexification. But see, Andy, you had
I think the picture that you can identify P plus with a holomorphic bit is there in the classical case as well. This is what leads to coming from Constant's version to the classical Borel file. There you do exactly this, so you identify P plus with a holomorphic or anti-holomorphic tangent space in order to relate Lie algebra cohomology to Dolbeau.
I see.
So it is there. It's just not that we use it often.
Yes.
Have you tried Chevalier involution?
No.
Just flip.
Something like this should work, and that to do the negative side, we shouldn't have to do everything again. It should be something like a Chevalier involution to bring you across. The real problem, though, is not reproducing this part here, it's producing this part here. I mean, it exists, but it's describing it and trying to find the relations of the cutiform exterior algebra. That's where the calculations come
It
in.
should be in the middle. It should be braided tandem product of algebras.
It should be. I mean, it's easy to say that. To actually turn it into a paper is more difficult. Yeah, it should be something like that. It should be the tensor product of the 0, 1 and the 1, 0, and then they're going to behave. But what is that braiding? How do these things come across? And you have to calculate. You have to show that this thing is also the same as this maximal prolongation. So, yes, that is how it should be, but there's a big gap between that and reality.
There is just techniques to unbraid it for the classical tensor products, and then
But then you have to try to put the differential on this thing here, and it's best really to describe the unit maximal prolongation first of all, and then afterwards try to get some more sophisticated braiding presentation of the thing.
Thanks. I guess time to thank the speaker again.